So far we have looked at pressure at varying depths within a fluid. Now in this section on buoyancy and Archimedes' principle, we will look at forces within the fluid. So first I want to go through 3 observations that tell us that there must be a buoyant force acting on objects that are either submerged or partially submerged in a fluid. So the first observation is here. If we're to release an object that is less dense than a fluid into a fluid, it will float, partially submerged in the fluid. So it will remain at rest here. That means that there must be an upward force supporting it, and that force is called the buoyant force. Secondly, if we're now to release an object that is more dense than the fluid into the fluid, it will sink, it will move downwards, but it's going to sink at a rate that's less than the acceleration due to gravity. So in a sense, it will fall more slowly than it would in air. And this shows that there must be a buoyant force or some kind of upward force acting on that object, and that is what we call the buoyant force. The last observation is if we were to allow this object to fall so that it reaches the bottom surface of the fluid, and then we could measure the normal force. Maybe there's a scale that allows us to measure the normal force acting on the object. We would find that the normal force is less than it is in air, so less than if we were to just place that object on a scale or on a surface in air. So that means as well that there must be an upward buoyant force acting on the object. And we'll see that this buoyant force is due to the difference in pressure at the top and the bottom of the object, so due to that pressure gradient. Let's look more into that now. Let's look at how the buoyant force depends on a fluid. To do this, consider a cylinder of some substance of height h and area A, which is immersed in a fluid, so that it looks something like this. We have the cylinder, its height is h, and then the pressure at the top of the cylinder will be P0, and the pressure at the bottom of the cylinder is P. Then this cylinder experiences a pressure force downwards on the top of the cylinder and a pressure force upwards on the bottom of the cylinder. Of course, there's pressure forces on the sides, but they would be equal and opposite, and they would cancel. So we know that P is greater than P0 since we looked at how pressure increases with depth. Then if we want to write these forces, we can use force equals pressure times area. And then based on this relationship, we can see that the force up from the bottom of the cylinder must be greater than the force down, which is at the top of the cylinder, since the pressure is lower at that point. The buoyant force is caused by the difference in these pressure forces. The buoyant force, Fb, equals F up minus F down. So this will be Pa, the pressure at the bottom times the area A, minus the pressure at the top, P0, times the area A. And from here we can factor out that factor of A, so we have P minus P0 times A. Okay, now I want to plug in the hydrostatic equation, P equals P0 plus rho F GH, for this pressure at depth H compared to the upper surface. So now I'll have the buoyant force equals P0 plus rho F GH minus P0 times A. And you can see that those pressures at the top of the region, or the top of the cylinder in this case, cancel. So we're left with rho, the density of the fluid, GH times A. And notice this height times area is just the volume. So we end up with this definition for the buoyant force, Fb equals rho F Vg. So when the cylinder is dropped in, or when an object is submerged in a fluid, it displaces a volume of water equal to its own value. This is true for any volume. It doesn't have to be a cylinder. So the volume of the object that is submerged under the water, it will displace a volume of water equal to that amount. So we can write this in one more way. I can replace rho Fg by the mass. The mass of the fluid will be the density of the fluid times its volume. So I also have the buoyant force equal to rho Fg. Replacing that, it is mFg. So Fb equals mFg. And from here we can see that the buoyant force is equal to the weight of the fluid displaced. And this is actually Archimedes' principle. Archimedes' principle says that a fluid exerts an upward buoyant force, Fb, on an object immersed in or floating in the fluid. The magnitude of the buoyant force is equal to the weight of the displaced fluid. So just to summarize, we've seen that the buoyant force here is given by Fb equals rho F, the density of the fluid in kilograms per meter cubed, times the volume, which is in meters cubed, and then times g. I put g over here, but we know that one. And then we've also seen that this equals the mass of the fluid displaced in kilograms times g. And this all gives the buoyant force in newtons, so either definition works. And here the volume V has two definitions. It's either equal to the volume of the portion of the object submerged. So if the entire object is submerged, it's the volume of the object. If only half the object is submerged, it's that half of the volume that's under the water. And this is equal to the volume of the fluid that's displaced when this object is submerged or partially submerged. So these two volumes are equal, and that is what Archimedes' principle says. Okay, now that we've seen how to define the buoyant force using Archimedes' principle, let's look at how to apply it to some Archimedes' principle problems. Example 12, an object is held beneath the surface of a fluid. The object has a mean density ρO and the fluid has a density ρF. Demonstrate the relationship between ρF and ρO if the object A floats, so rises, B sinks, or C stays put when released. All right, so if the object is floating for part A, it's moving up, that means that the buoyant force is greater than the force of gravity so that it can accelerate upwards. So we'll have the net force in the y direction greater than 0 to mean that there's an upward acceleration since it's starting from rest. So we have the buoyant force minus Fg is greater than 0. So this means, as I was saying, that the buoyant force is greater than Fg. And we want to find a relationship between the densities, so let's write each of these forces in terms of the density. So I'll have ρF, the density of the fluid for the buoyant force definition, volume of the fluid displaced, and it's completely submerged, so that's the entire volume of the object, is greater than the weight of the object. So for the weight of the object, we can write the mass as ρOV, so this is all the mass of the object, and then times g. So notice here that the volumes will cancel, and this factor of g cancels, and we're left with the density of the fluid is greater than the density of the object. And this is what we would expect, right? If an object is less dense than the fluid, when it's dropped into the fluid, it will rise upwards. Okay, so now let's consider the case where it sinks. So it's going to accelerate downwards when released from rest in the fluid. Now the buoyant force must be less than the weight for it to have a downward acceleration. And basically I can repeat this derivation here. What will change is my sign. This inequality sign will now be less than. We'll want our net force in the y direction less than 0. And following down the same thing, we'll have Fg minus Fb, or Fb minus Fg is less than 0, and we'll end up with this relationship here, which will tell us that the density of the fluid is less than the density of the object if the object sinks. So now we know that objects more dense than the fluid will sink in the fluid, which is what we would expect. All right, now let's consider the last case where the object stays at rest when released in the fluid. In this case, its net force would need to be equal to 0. So the net force in the y direction equals 0, meaning that the buoyant force equals the weight. And following the similar logic To above, we have the density of the fluid times the volume times g. It's the density of the object times the volume times g. And then these cancel, and we end up with the densities being equal. So the density of the fluid equals the density of the object if that object is completely submerged, released, and then just stays where it is. Example 13, a block of wood of density 540 kilograms per meter cubed is dropped into water. The wood has a cross-sectional area of 100 centimeters squared and a thickness of 15 centimeters. A, how far will the block submerge into water? B, how much mass would you have to add on top of the wood so that the surface is just at water level? All right, so it looks something like this. We have the density of the object, the density of the fluid, which is water, the cross-sectional area of this object, and then its thickness, which is 0.15 meters. So we're looking for the height that actually submerges into the water. So you should start all of your buoyancy problems when an object is at rest with the net force in the y direction equals 0. We know that the weight is acting downwards and the buoyant force is what is supporting the object in the fluid. So FB minus FG equals 0. We have FB equals FG. And just like the last question, let's plug in the expression for each of these. The buoyant force is going to be rho F times the volume of the fluid displaced or the object submerged times G, which equals the mass of the object times G. Now we can plug in for the mass of the object because we don't have the mass, but we do have its density and its dimensions. So we'll use mass of the object equals the density of the object times its volume. So we have rho F VFG equals rho O VOG. These volumes are not equal this time because the object isn't fully submerged. So the volume of the fluid displaced is equal to the volume submerged, which is just this portion of the object. Okay, G does cancel though. So then I'll have the density of the fluid times, for the volume we can put in the volume of the fluid submerged will be H, this height, times the cross-sectional area A. So AH equals rho O times the entire volume of the object, which will be that thickness, 15 centimeters, times the cross-sectional area. And then the areas cancel. So I end up with H equals rho O over rho F times the thickness. So we get 540 kilograms per meter cubed over 1,000 kilograms per meter cubed times 0.15 meters, which is 0.081 meters. So 8.1 centimeters of the object is what is submerged, this height here. So we find that the amount submerged is proportional to the ratio of the densities between the object and the fluid. All right, now in part B, there's going to be an extra mass added so that this object completely submerges, and there's an extra weight on top of it. So our free body diagram will be the Fg of the object of the wood, that Fg of the added mass, which is not submerged at all in the water, and then the buoyant force, which is supporting both. And again, we need to have our net force in the y direction equal to 0. So this time I have Fb, which is up, minus Fg of the object, minus Fg added, equals 0. So let's plug in to find this. We'll have our buoyant force, which is going to be the density of the fluid, times the volume, entire volume of the object this time, and then G, minus the density of the object times its volume times G, as we did in part A, minus the mass added, M added, times G. And right away we can see G cancels, it's in every term. And this mass added equals rho F V minus rho O V. And then we can pull out this volume, so that will be rho F minus rho O times V. And since the entire, we can do this since the entire object is submerged, so the volume of the fluid displaced is equal to the volume of the object this time. That's why I haven't added subscripts. And then this will be equal to rho F minus rho O, area times height. Okay, made a bit of extra room here, so then we can plug in here. This will be the density of the fluid, 1,000 kilograms per meter cubed, minus 540 kilograms per meter cubed, times the cross-sectional area, 0.01 meters cubed, times 0.15 meters, the height, which is entirely submerged this time, or the thickness. And this equals 0.969 kilograms for the mass that needs to be added in order for the object to fully submerge. Example 14, what radius must a helium balloon attached to a 200 kilogram basket have to float with neutral buoyancy in the air? Assume that the balloon itself has a negligible mass and that the basket is sufficiently small that its buoyancy is negligible. Alright, so in order to do this, we have that table that we'll need to use to find the density of air and the density of helium. The density of air is 1.28 kilograms per meter cubed, and the density of helium is 0.017 kilograms per meter cubed. Now, the assumption that the balloon itself has negligible mass and that the buoyant force of the basket is negligible essentially means that the forces that are shown on the free body diagram in the question are the only forces we need to consider this time. So we have the buoyant force of the helium within the balloon, the weight of the basket, and then the weight of the helium. Now we're told that this balloon floats with neutral buoyancy. This means that it's floating at rest so that it is not accelerating. So this is neutrally buoyant. We have the net force in the y direction equals to 0, and we can start with that. We have the buoyant force minus the weight of the helium minus the weight of the basket equal to 0. And then we'll plug in the buoyant force is the density of the fluid, which is air since it's submerged in the fluid, so submerged in air. The volume of the balloon, I'll just leave it as V, G, minus the density of helium, the volume of the balloon. It's the same volume because the balloon is completely submerged in air, G, so this is the mass of the helium here for this term. And then minus the mass of the basket times G equals 0. And we're looking to find eventually the radius of the balloon. So how we can do that is by solving for the volume of the balloon, and then when we have that, we know that it's a sphere, so we can find the radius. So the volume is our unknown. Okay, so I will have rho air, Vg, minus rho helium, Vg, equals the mass of the basket times G. And let's cancel G now. Could have done it in the previous line as well since it's in every term. Then I'm going to factor out the volume of the balloon here, density of air minus density of helium times the volume equals the mass of the basket. So the volume is equal to the mass of the basket over the density of air minus the density of helium. So this is going to be 200 kilograms over 1.28 kilograms per meter cubed minus 0.17 kilograms per meter cubed, which is 180 meters cubed. So we have the volume, and now since it's a sphere, we know the volume equals 4 over 3 pi r cubed. So rearranging for r, I have r is the cubed root of 3v over 4 pi. And then we can plug in numbers again at that step. So the radius will be the cubed root of 3 times 180 meters cubed divided by 4 pi, which is 3.5 meters for the radius of that helium balloon. Example 15, when a crown of mass 14.7 kilograms is submerged in water, an accurate scale reads only 13.4 kilograms. Is the crown made of gold? So the idea here is to use the buoyant force in order to figure out the density of gold, and then we can compare to the known density of gold to see if it really is gold. So the density of gold is 19,300 kilograms per meter cubed. So let's use this setup in order to find the density. There's a spring scale here, so normally if this crown was in air and if it was attached to a spring scale, this tension force would give a measure of the weight, and that would give then the mass of the crown. And when this is done in air, the true mass is found to be 14.7 kilograms. Now it's submerged in water, and instead there's a new reading of the tension on this scale, which gives the apparent mass. And the apparent mass is 13.4 kilograms. So this goes into the tension. The tension is this M apparent times G, in this case when it's submerged in water. We generally measure the mass of objects, what we call the true mass to be, is in air, and though there is a buoyant force in air, for objects of low mass, that's really negligible here. Okay, so let's look at this case. We have the net force in the y direction equal to 0. So Ft plus Fb minus Fg equals 0. So we're going to have that M apparent times G for the tension force. Now the buoyant force is the density of the fluid, which is water, the volume of the crown times G, minus its true weight, which is the mass in air, this M true, times G equal to 0. So let's solve for this unknown volume, and then we can use the true mass to find the density. All right, so rearranging, canceling G first, and then we can rearrange to find the volume equals the mass, the true mass, minus the apparent mass divided by the density of the fluid, which is water. So that's going to be 14.7 kilograms minus 13.4 kilograms divided by 1,000. So 1.3 times 10 to the negative 3 meters cubed. So then the density of this crown will be the true weight, the true mass, 14.7 kilograms, over its volume, which doesn't change, 1.3 times 10 to the negative 3 meters cubed. So I'm using density is true mass over volume, and that gives 11,300 kilograms per meter cubed, whereas we were expecting 19,300 for gold. So no, this crown is not really gold, and if you look at the table of densities, you'll see that maybe it's lead. That looks like the density of lead. Example 16, what is the likely identity of a metal if a sample has a mass of 63.5 grams when measured in air and an apparent mass of 55.4 grams when submerged in water? All right, so this is similar to the last question. We can imagine that a spring scale is used, or any kind of scale would have this upward force that measures the apparent weight. So we can call it the tension in this case and imagine it's like the previous example, or you could call it the normal force if you're picturing it resting on a standing scale. So we have the sum of the y forces equals 0. We'll try to find the volume again so that we can find the density, and this time use the density to identify the metal. Okay, so Ft plus Fb minus Fg equals 0. And then Ft is the apparent weight. So we'll have m apparent times g plus the buoyant force, the density of the fluid, which is air, times v times g, minus the true weight, so the true mass times g equals 0. We can cancel g right away and then solve for the volume. So the volume will equal the true mass minus the apparent mass divided by the density of the fluid. So we'll have 63.5 grams minus 55.4 grams over 1 grams per centimeter cubed. That's the density of water in grams per centimeter cubed. Okay, I've just filled that in here, so this gives a volume of 8.1 centimeters cubed. And then we can find the density using the true mass over the volume, 63.5 grams over 8.1 centimeters cubed, which is 7.84 grams per centimeter cubed. And then if you check the table of densities, this looks like it's iron or steel.